Okay, to tie the last two sections together, again, the conditions are f of a must exist, the limit of as x approaches a of f of x also must exist, and f of a must match the limit of f of a. So the two have to agree. So what we're going to do is we're going to do a couple quick things. We're going to say, does the limit, is there continuity? Is this graph continuous at this point right here at A? We would say, does it match for condition 1? Condition 1, check. It exists. Condition number 2, does the limit exist? Does it seem to be going to the same place as you approach it? Check. And does it seem to be, does number 1 seem to be equal to number 2? And that's going to be, of course, condition number 3, check. So in this case, it is continuous at A. And in fact, this function is continuous over the entire function. In this case, it is not continuous at A, because although it has a limit, we can stop right here. It fails condition number 1. It's done. Don't even need to go any further. It fails condition 1. This, it doesn't exist because, again, we have an asymptote at 0. So if I take the limit as x approaches 0 of f of x, the answer is does not exist. It fails condition 1. It fails condition 2 because it goes opposite directions. And so therefore automatically it fails condition 3. Now, down here at the bottom we have the limit of f of a. Does it exist? So number 1, we're good. Number 2, at 0 it fails. So we're done, and automatically, since 2 fails, 3 fails. Up here we have condition number 1. It exists. Check. Condition number 2. The limit exists. It seems to be going to the same place. Check. The problem is number 3. The two do not match. It fails. So the only one for which there actually is a limit is the very first one. Well, I'm sorry. Continuous is the first one. Again, if we were to name these, we have a jump discontinuity, asymptotic discontinuity, removable or point discontinuity, and that is continuous. Now, let's look over here at this guy. We don't have to just look here, because we can already determine that this is going to fail the continuity test by rule number 2. The limit doesn't exist. Same thing's going to happen here. This is a rule 2 failure. However, the limit totally exists, and it is continuous at this point. I don't know, call it -7. It does exist, because does it pass number 1? Check. At this point only, does it have a limit? Number 2. Check. And do the two agree? Condition 3. Check. So we could say it's continuous at this point, just not continuous over the entire thing. So those are our conditions and our tests for continuity. There is one more I do want to show you, and that is this guy right here. This graph is f of x equals 1 over x squared. It's a lot like 1 over x, but because of the squared, everything turns positive. Well, at this point, it's continuous. Yes, yes, exists, they agree. Here, yes, yes, exists, they agree. Over here, yes, the limit exists, the graph exists, they all agree, it's all good. However, at 0, we have a small problem. First of all, f of 0 does not exist. But interestingly enough, number 2 checks out. Because where do you seem to be going from this side? Positive infinity. Where do we seem to be going from this side? Positive infinity. So in this case, they seem to match. So number 2, we would say the limit as x approaches 0 of f of x, we would say is positive infinity. So it does exist, and of course condition number 3 does not, because condition number 1 doesn't exist. But we do indeed have a limit here, kinda. It technically doesn't exist because you technically can't get to positive infinity. But rather than saying, yes, indeed, both sides do match, and yes, indeed, they both go to positive infinity, but no, since you can't go to infinity, the limit is in a technicality non-existent. Instead of saying that, we simply say the limit is positive infinity. Now, there is one other type of limit not connected to continuity that we need to talk about. This graph here, we have its end behavior. As x approaches negative infinity, y seems to be approaching, well, flattens off, 0. What end behavior is really a limit. What we're saying is the limit as x approaches negative infinity of f of x, as it approaches this way, where does it seem to be going? 0. It seems to be going towards 0. This is the x part. This is the y part. So this end behavior is really just a limit in disguise. Same thing, the limit as x approaches positive infinity of f of x. In this case, as it goes forever this way, it seems to be going toward 0. So it would apply if you had the same thing. In this case, the limit as x approaches positive infinity of f of x is going to be positive infinity. At limit as x approaches negative infinity is indeed negative infinity. So, in behavior, continuity and limits, all of them have to go together. It's just like a giant bowl of mathy spaghetti.